All right, everybody. So what we're going to be looking at today is section 1.3 in your textbook, and this section is called Logical Equivalence. Okay, and so in order to do that, we're going to have a few definitions here. And so let's look at them. So a compound proposition, which we studied in the previous section. Remember, a compound proposition is just a proposition made up of other propositions. So like, for example, like P and Q implies R, for example. That's a compound proposition. Just any proposition that involves propositions plus those operations, like and, or, the conditional, exclusive, or, all of those. Okay, so any of those are compound propositions. And if you if you look at the truth table for it, and you get that it's always true. So when we say always true, what we mean is that you have the entire column is going to be trues in the truth table. So all t's, that's too much, all t's in the truth table. And if that happens, that's a tautology. Okay? Now, if you find something that's always false, a compound proposition that's always false, then that's called a contradiction. Right? So always true is a tautology, always false is a contradiction. Right? And if it's not a tautology and it's not a contradiction, so not a tautology, not a contradiction, so it's not always true, not always false, then it's called a contingency. So that's something that's sometimes true and sometimes false. Some T and some F in the truth table. Okay? And so we know what a tautology is, we know what a contradiction is, and now we know what a contingency is. Now, almost nobody is going to be asking you about contingencies. We're going to be interested mostly in tautologies. Okay. Now, once we have that, we can use the definition of tautology to come up with the definition of logically equivalent. And remember that this section is called logical equivalence. So that is very important. So P and Q are logically equivalent, right? So P and Q are logically equivalent. I don't like that. There it is. If P implies Q is a tautology. And the symbol we use for it is this right here. So like an equal sign, but with 3 lines in it, gets used for various things in mathematics, just depending on what subject you're in. In a lot of subjects, it means congruence. And congruence is basically if two things are, kind of equal in some sense, but they're equal in some sense that's not actually equal. So that's why it looks like an equal sign, because we want to say that they're equal, but there's no concept of equality, and so this is like equality, but it's not equality, and so in this case it's logical equivalence, but they don't want to use an equal sign, and so they use this sign instead. Okay, now what we're going to do is we're going to look at a bunch of logical equivalences, because what we want is this. So the idea behind this section is we're going to learn in this section, you're going to learn how to check if things are logically equivalent, yes, but that's not the main goal. The main goal is to actually learn a bunch of things that are logically equivalent to each other. So in this section, we learn some common I'll say important equivalences. Now, why would we want to learn some equivalences? So the idea is that if you have a statement, a logical statement, and you want to be able to manipulate it, so you know how to manipulate things with algebra, right? How to simplify things with algebra. Well, we want to be able to simplify logical expressions kind of the way we do algebraic expressions. And in order to do that, we need some rules, how to simplify things. And the way you simplify them are logical equivalences. So let me say that. So common important equivalences. So the idea is these will be our rules the algebra rules that you use to simplify equations. Okay? And so that's what we want to learn them. Now we're not going to really use them very much in this section, but in the next section, which is going to be predicates and quantifiers, I guess actually 2 sections away, nested quantifiers, 1.6, what's 1.6? It might be several sections away, but when we get there, at some point we're going to be needing these. Okay, so for now we're just going to learn what logical equivalence is and prove them, but then at some point we're going to want to be familiar with them. So the first 2 we're going to look at are called associative laws. So notice that I'm calling them laws, right? Like associative law, just like there's an associative law for algebra. So like in algebra, the associative law is this, right? Like if you have if you have like A plus B plus C, that's actually the same thing as A plus B plus C, right? This is associative rule for addition. And now look at this. So here you've got like P or Q or R, and here you have P or Q or R. What's the difference? The difference is where those parentheses are, right? Right here, the parentheses are around the P and the Q, and here they're around the Q and the R, just like the associative rule for addition. And again, you could technically use the associative law for addition to help you do algebraic simplification. And that's what we're going to use it for, but it won't be for algebra, it'll be for logical expressions. Okay, so we want to use truth tables in order to show that these things are associative, or sorry, to show that these things are equivalent. So how do you do that? So do I have enough room to do 2 truth tables here? I think I do. Let's do A. So the way you would show logical equivalent with the truth table is really there's 2 different ways. And one is just an extra step. And since it's an extra step, it's not actually even required here. But what you do is, let's look at this. We have a P, a Q, and an R, right? So hopefully you remember from last time that that's going to mean we need 8 rows in our truth table. I just figured out why I can't draw straight lines. I never could last time, right? It's because we need these. Oh, I can't add them. Okay. I can't add lines to the paper because this is a PDF. Oh, that makes me sad. Okay, but that's what's missing. All right, so we have P, Q, and R, and then in order to do this, think about doing the left-hand side first. If I'm going to do that left-hand side, I'm going to need to evaluate P or Q, right? And then after I evaluate P or Q, I'm going to need to evaluate P or Q or R, okay? And at that point, I'll have this left-hand side done. But we also need to look at the right-hand side. So somehow we have to get to the right-hand side. So what you're going to have to do is same thing, but you're going to need to get the right-hand side. So for the right-hand side, you need Q or R. So we're going to evaluate Q or R. And after we evaluate Q or R, then we're going to do P or Q or R. Right? And when we do all that, we're going to be able to tell whether or not these are logically equivalent based on whether or not the two columns that are highlighted now are the same. Now that's not actually what it says up here, right? It says logically equivalent if P, if and only if Q is a tautology. Now the thing is if and only if, remember that if and only if, what it means is that the symbols match in the table, right? Either they're both true or both false. P and Q match, basically. The true and the falses match. Well, the true and the falses will match if you actually have the exact same columns in these two columns. So you don't even need to make that last column, and I would recommend that you don't. I would recommend that you just do exactly what I wrote here. And we're going to compare these two columns when we're done. So let's try it. So what do we got to do? Well, we've got PQR, 8. We're going to need 8 different rows. So we know that the way you start, if you have 8 rows, is 4 trues, 4 false. After you have that, then you're going to go 2 trues, 2 false, 2 trues, 2 false. And then for the third one, true, false, true, false, true, false, true, false. Okay, and I need to make some lines on here because if I don't, it'll be very messy. It's already going to be kind of messy because I'm messy. We don't need to make it any worse. Okay, so here's our truth table. Now we will get started. So you have to remember the rules for truth tables, right? So when you're doing an or, remember that any true makes it true, right? The only time an or is false is when they're both false. So we're doing P or Q. So we're looking at true or true, true. True or true, true. True or false, true, right? The only time it's false is when they're both false. True or false, true. False or true. Actually, let's go a little bit faster here. False or true, true. False or true, true. False or false, false. False or false, false. So the last two are true, true, and then false, false, where the two falses are. Okay, so there you go. Now once I have that column, then I need to do this column here. How am I going to do that? Well, it's going to be an or. It's going to be an or with this column and this column. So we do another or. So how does it work? Well, I mean, again, only going to be false when there's two falses. So take a look at these. No, that's true, true, false, true, 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 false, true, 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 false, true, true, false, 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 right? The only time we go false, false is that very last row. So this one's going to be false, but all of the others are going to be true because only false, false is false. Okay, so there you go. There is one of the two columns that I need. Then what you're going to do is, you know, the remaining two columns. So we need to do this one now, Q or R. So Q or R, we're going to be looking at these two. Let's just highlight them temporarily. All right, same deal. This is an or, and so for an or, we need two falses to come up false. So take a look at them. Where do we have two falses? True, 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 false, false, true, false, false. Hey, there's a false. True, 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 false, false, true, false, false. Here's another false. Right? So we only have falses where there are two falses on the left side there. The rest are true. All right, now what we need is we need to do an OR between P, here's P, and Q or R, here's Q or R. And again, only false when there's two falses. So you've got true, 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 false. So far they're all true. False, true, false, true, false, true, false, false. So that's a false. But the rest of them had one true, so they're all true. Okay, so that's how I fill out this truth table. Now once I fill out the truth table, remember what we're actually looking at here is we're supposed to be comparing this column and this column. And if they're the same, then those two things on top are logically equivalent. So you're supposed to be able to look at this and say, because the columns for P or Q or R and P or Q or R with different parentheses are the same, we say P or Q or R is logically equivalent to P or Q or R. Or if you want to write the symbols, P or Q or R logically equivalent to P or Q or R, like that. Okay, so that's how you test logical equivalence. If the two columns are the same, then they're logically equivalent. And I don't want to do it, but basically, if you added one more column here, and then you took this, sorry, not that actually. So if you put like P or Q or R if and only if P or Q or R right here, and then you made another column here, then what would happen is you would just be checking if the two things matched, which of course the columns are the same, so they do match. And that would mean that you get trues all the way down because you're just checking if they match. And that would be a tautology. So that's the tautology that they're talking about when they say, when they write it this way, P if and only if Q. But you don't need to do that. You just need to, back it up. Oops. You just need to back it up and say, if the columns are identical, then the two columns are logically equivalent. All right. So there you go. That's how you check that two things are logically equivalent. So you make the truth table for both of them and make sure the truth tables are the same. Okay. So if truth tables for P and Q, now whatever P and Q are, right? Not actual P and Q, compound propositions P and Q. So if truth tables for P and Q are the same, then logical equivalence. Okay? And that's the idea. Now, if you look at part B here, you do it very much the same way, but I'm not going to do that one because it's almost the same exact work again. You just have to make another big truth table. And we're making plenty of truth tables in this lecture, so, one is enough for this. So let's do another rule, De Morgan's laws. So De Morgan's laws are very important, like very, very important. So I know it's written right there, but I just want to say something about it. So the idea is, like, in algebra, if you have like a negative outside of like x plus y, right? You know that you just distribute that minus sign, right? And it becomes negative x, I'll say plus negative y, right? They both get a minus sign because you just take that and it gets distributed. Okay, that's how it works in algebra. Well, in logic, it's a little bit different. It's a little bit different because when you have a negation outside a p and a q, the negation does distribute, so it's not p, not q. So that looks the same as algebra. But what's different is the symbol in between. The symbol here, you have an and. When you do, when the negation distributes across an and, it actually becomes an or. And that's weird. But that's what happens, okay? And so whenever you want to do that rule, like an algebra rule for simplifying things, you have to know the negation ends up distributed, but the symbol flips from an and to an or. And that's De Morgan's law. Okay? So how would we show that that's actually true? How do we show it? Well, guess what? We make another truth table. Now, thankfully, it's going to be a shorter truth table than before because it's just P and Q instead of P or Q or R. So let's make the truth table. So hopefully it'll look a little nicer to you this time. So we go P, Q. In order to do this, I'm going to do a P and Q. Then I'm going to do a not P and Q. And this will be, of course, the left-hand side. We're also going to be looking for the right-hand side. So we're going to need a not P, a not Q, and then a not P or not Q. And then we'll be comparing those two columns, the ones that are highlighted. If they're equal, then those two things must be logically equivalent. And of course, you can probably guess that they are going to be equal, because if not, then De Morgan's law is a lie. So we only have P's and Q's, so we only need 4 rows, not 8. So we'll go true, true, false, false, true, false, true, false, and we can get started. So let's go ahead and get started. So we got, we're doing an and. So remember how ands work? Ands are only true when you have a true, true. Otherwise, they're false. So true, true, that's true. So you have to remember these from before. True, false, that's false, right? True and false is false. False and true, false. False and false, false. So you're basically just remembering that truth table from before. Then what we're going to do, though, is we need to do not this. But P and Q is actually this right here. So we just need the negation of this whole column. So we're just going to take these symbols and reverse them. And that's how you do the negation. So true is going to become false. And we have 3 falses that are going to turn into 3 trues. There you go. False, true, true, true. And that's that column. So now we'll move on and do the other side, the right-hand side. So we have not P. So we're going to take the P column and reverse it. So it's going to be, what is it going to be? It's going to be false, false, true, true. Then we've got not Q, so we need to take the Q column and reverse it. So instead of being true, false, it'll be false, true, true. And then we need to do an OR between these two. So we're looking at these two columns, and what we're doing is an OR. And remember what an OR does? OR is only false when you have two falses. So when we're looking at this, we've got false, 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 false. False or false is false. False or true, true or false, true or true, 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 right? All of these are true because they have a true in it. True, true, true. Right, so we got that. Now what are we going to do? Well, we need to compare this column to this column. If they're the same, then those two things are logically equivalent. And of course, they are. So we can say, so we see not P and Q is congruent to not P or not Q. And that's actually what we were trying to verify. There you go. So that's done. So again, remember what the point is, right? The point of this is that when the negative distributes, the symbol flips to the other symbol. So instead of an and, it's an or. Now let's look at the other De Morgan's law. So the other De Morgan's law is really the same rule, but the difference is that this one, right, had an and on the left or on the right. Well, it works the other way too. Or on the left becomes and on the right. So however it is, you just flip the symbol, right? So when you're trying to work this out, you just say like, oh, well, what is that equal to? Well, you go not P, not Q, and then what symbol is it between them? Well, it was an or, so it turns into an and. And that's De Morgan's law. Okay, so let's do the truth table, see how it goes. P, Q, what are we going to need? We're going to need P or Q, it looks like. And then we're going to need not P or Q. Missed some parentheses there. Then we're going to need not P. Not Q. Oh, that's crooked. And then finally, not P and not Q. And as before, we are going to be looking at two columns here. This one is going to be right here. This one is going to be right here. And if they match, they're logically equivalent. So we'll do this a little bit faster because it's very similar to the previous one, of course. So we go true, true, false, false, true, false, true, false, and then we have P or Q. So it's an or, so it's only going to be false when you have two falses, so that's right here, and the rest must be true. Then for the next column over, you just have the negation out front, so we're going to reverse that, so it's going to be false, 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 true. All right. Then we got this column here. It's the negation of P. So we're going to be looking at the P column and reversing it. So instead of true, true, false, false, it's going to be false, false, true, true. Then we've got not P, so we're gonna, or sorry, not Q, so we're gonna reverse the Q column. It was true, false, so it's gonna be false, true. And then we need to do an and between those. And. So have to remember how an and works. How does an and work? An and is going to be only true when you have a true and a true. Right? So only true when you get true and true is true. So what's that mean? So that means we've got false, false. That's false. False, true. That's false. True, false. That's false. True, true. So true, true. True and true is true. All right. So then we look at this column here, and we're going to compare it to the other one here. And of course, they're the same, which means that we did verify that identity, right? Logically equivalent. So this one, not P or Q, is logically equivalent to not P and not Q. And that's the other De Morgan's law, which I don't know why I'm writing it. It's written on the page, but there you go. So both of those are De Morgan's laws together. And they deal with how a negation goes across a sum. Okay, now here's the thing. There's a lot of these, okay? So look at these. I printed the table here. This is straight out of your book. So table 6 out of your book in section 1.3. So this is in section 1.3. And I will explain a little bit about them, but not too much here. Like this right here, P and true is P. Like you can make a little truth table for any of these, and you know, they're very easy to verify. Like if I go P, and the true is a little bit weird, but I can make like a column for true, and P will be true or false. True is just going to be true, right? We're not like true is not ever going to be anything but true. And then you would check what P and true is. Well, remember how this works. P and true, so true or true is true, false and true is false. And if you look at these two, and you look at these two, like they're the same, right? So whenever you do an and with a true, it's like you didn't do anything. P and true is just P. And so you can make a little truth table for every one of these in this whole thing, but I would not bother doing that, and you just kind of want the rules. So these are called identity laws because it's like multiplication, right? Like, so the equivalent would be like in algebra here. What these are equivalent to is like if you do like x times 1, you get x, right? Or if you do x plus 0, you get x, right? So those are, so 1 is what we call the multiplicative identity, and 0 is what we call the additive identity. And that's why these are called identity laws, because the identity is the operation that leaves you with what you started with, right? The operation that doesn't do anything is the identity. Okay. So the next two are called domination laws. And the reason they're called domination laws is because if you do P or true, right, it doesn't matter what P is, the result is true. So like the true dominated the P. So you don't see the P anymore. When you do P or true, you just get true. when you do P and false, you just get false, right? It doesn't matter what P is, so the P was dominated. What would that be in algebra? Well, mostly it would be something like this, right? If you did like x times 0 equals 0. It doesn't matter what the x is. After you multiply by 0, you're just going to get 0. Okay? So that's the equivalent of that. Idempotent laws. There's nothing really there. You can just look at it. P or P is P. P and P is P. I mean, that just makes sense, right? You can work it out. It's not really anything to do, but you can do that. Double negation. That probably makes sense, because remember what negation does? Negation just flips truths to falses. So if you change the truths to falses and then you change the falses back to truths, then you're going to get back to where you start. So double negation gets you back to where you start. That makes sense. Commutative. Commutative is where you change the order. Well, let me write this, by the way. So like a double negative, right? If you do negative x, that's just x. That's what that is. Commutative, that just means you can change the order. So that's like x plus y equals y plus x, or x times y is y times x. That's commutative. Okay. Associative, we already looked at associative. Kind of want to make this a little bit smaller or something. I don't know how to do that. I'll just move it up a little. Okay. So associative means you can change the parentheses, which is changing the order that you do the operations. So that's the same as algebra, right? If you do x plus y plus z, that's the same as x plus y plus z. Or in multiplication, x, y, z is equal to x, y, z. So associative. Distributive. Okay, kind of running out of room here how to do these. But distributive here, I guess I could do it on the other side. Let's do it on the other side. So the equivalent of distributive is going to be the distributive rule for algebra. So like if you do x times y plus z, that's xy plus xz, right? Like basically you distribute the x. And so if you look at this, if you take the p on the q and the p on the r, right? P on the q, p on the r. Yeah. And then the way the operations go is, so if you look here, this operation between x and the y, like between x and everything else, is multiply. So between x and the y is multiply, and x and z is multiply. And then the inside operation is a plus, and the inside operation is a plus. The same thing is true over here. The inside operation is an and, so the inside operation is an and then you have P or Q, so P or Q, and then you have P or Q, and then you have P or R. P or R. So it's the same as the distributive law that you have in regular algebra. Distributes. De Morgan's law we already talked about. There is no De Morgan's law for algebra. And then you have absorption laws. Absorption laws. Again, the reason this is called absorption is because you have this thing over here, right, which is pretty complicated looking, and then somehow the Q is absorbed. You do P or P and Q, and then somehow the Q doesn't even matter, and you're left just with P. Okay. Yeah. So there you go. And then we have negation. Negation laws. Those are weird. They're not actually weird. They're very simple. But the idea here is when you're doing an and, right, you have to have two truths. Well, if you look at the truth table, right, if you have P, not P, and then you do P and not P, actually let's do P or not P as well. Let's do the other one, P or not P, right? You go, okay, well, true, false. We only need two because there's only P is involved. So not P is false, true. And then if you do an and, in order for an and to be true, you need two truths. But we have true and false, right? We have true and false. That's true. False and true. Oh, wait. I wrote that wrong. So we have true and false. That's false. You need two truths to be true. False and true. That's also false. Now the other one, with an or, remember that an or is true whenever either one is a true. And so true or false here, true or false is true. False or true is true. So what you see is that this comes up false no matter what. And you see that this one here comes up true no matter what. And that's what this says, right? When you do an or, you get true no matter what. And when you do a false, when you do an and, you get false no matter what. So one of them comes up true, one of them comes up false. Just what we show in the truth table. Okay. And so those are the ones that have names. And then there's a whole bunch of other ones that don't have names, and we're not going to talk about very much at all. But here they are. Logical equivalences involving conditional statements. Now, what these are for is, in logic, an if-then statement here, an if-then statement can actually be rewritten just with ands and ors. So you can turn conditional statements into ands and ors, and of course you could go back the other way if you need to. And so that's what these are mostly about, is turning conditional statements like this into statements that don't have an if-then, they just have ands and ors. All right. So just, you can do that stuff. And so these are kind of like complicated algebra rules that you could look up if you ever needed them. And same thing for involving biconditional. Biconditional is just the if and only if thing. Okay, so that is this section. Okay, now what I want to do though is I want to pick a couple questions out of the book and just work through them, and so you can see what the homework is like for this stuff. So let us do this. So I'm going to pick a couple from the book. So you have to do 1 and 3 on your homework. So we're going to look at number 2. 1.3.2. So I'm just looking at the book, and let's find one. Okay. Okay, very simple, right? So it just says show not P and P are logically equivalent. All right, very simple, right? We already know how to do this. Let me, I think I picked bad paper. Yeah, that's better. So we want to show that these two are logically equivalent. Of course, there's not much to it. You just make a little truth table. You're just going to go P. I hope you're not actually going to go P. I'm not. And then you need not P. And there you go. And we'll be comparing this, which is right here, to this, which is actually right here. So this is a very simple one. So you just go true, false. And then not P is false, true. And then if you do not that, you're going to reverse the signs again. And of course, this column and this column are the same. So you just say, oops, this and this, same, so P is logically equivalent to not P. And that's all there is to it. So that's how you do logical equivalences. Obviously, this was a very easy one. All right. Verify the distributive law, verify De Morgan's law. We actually did De Morgan's law already. Okay, yeah. So there are some involving English. So let's look at that. So you have to do 7 and 9. And so let's look at 8. 1.3.8. So here's what it says. It says use De Morgan's law to find the negation. And this is the one where there's A, B, C, D. We're going to do 2 of them. I'm not going to do more than 2. So let's see, A. Kwame, probably Kwame Brown. I think that's probably who that is. Basketball player. Kwame will take a job in industry or go to graduate school. I recommend graduate school. You get up later. Okay. So here's the idea. Here's what you need to know. De Morgan's law. Okay. So what we want to do is this. Let me write in a different color here. So we want to negate this, right? I don't want to write it in symbols because I'm lazy. But we want a negation around this. Duplicate. Come down here. Hooray for technology. All right. So we want a negation around this. Okay. And the whole point of De Morgan's law is what happens to this, right? Kwame will take a job in industry or go to graduate school. And we want the negation. So according to De Morgan's law, right, what you do when you negate an and or an or is the negation, oops, very too big. How do I make it smaller? So when you do a negation, they both get a negation, but remember what happens to the symbol flips. If it was an and, it turns into an or. If it was an or, it turns into an and. So we need to flip that symbol. Well, in here, we're not going to flip the symbol, we're going to flip the word. Okay, so we need to do this. We need not here. So this is going to flip the symbol or switch the symbol. Switch to and for De Morgan's law. And also you have to negate both the P and the Q. So the negation here would be something like this. You would say Kwame will not take a job in industry. That's my not P. And the or is going to switch to an and. That's because of De Morgan's law. And he was going to graduate school. We need to negate that. So now he's not going to go to graduate school. And not go to graduate school. So you see, they both get a not. That's distributing the not. And also the or turns into an and. Right? That. So Kwame will not take a job in industry and not go to graduate school. I should say I should write that in better English, and I should say will not go to graduate school, right? Let's move this. Okay, and that's it. That's your answer. Right, and the goal, let me say it, right, remember not P or Q turns not P and not Q. So they're both negated, and the or turns into an and. Okay, let's do one more of those, just in case that was confusing, I don't know. So that was 1.3.8a. Let's do 1.3.8 C. Okay. 1.3.8 C. C. So it says James is young and strong. I am old and weak. All right, James is young and strong. Okay, so I'm going to do this one a little bit more in depth than the other one. You could probably figure it out, but think of it this way. This is I'm just rewriting it. James is young. Think of it this way. And James is strong. That's really what we're saying here, right? James is young and James is strong. And we want to negate it. We negate it. So we're going to have a negation on the outside of James is young and James is strong. Okay, now we need to apply De Morgan's law. So we're going to apply De Morgan's law. How does that work? Well, the way that works is this is going to be distributed. So it's going to go here and it's going to go here. And this, the and is going to switch. So we applied De Morgan's law, and this is going to be not James is young. The other one gets a not James is strong. And in between them, we had an and. Now it's going to be an or, because that's what De Morgan's law does. So you have not James is young or not James is strong. So let's apply those negations. So you apply those negations, and what is not young? If you can think of a word that will work, use it. If not, just say James is not young. That's fine. Or, and then we need James is strong, the negation. What's the negation of strong? You could say weak, but, you know, I mean, maybe he's in the middle, right? Maybe if you say weak, you're saying there's only two choices, strong and weak. Maybe there's like strong, weak, and in the middle. And so maybe he's not strong, but maybe he's in the middle. So it's probably best to say just James is not strong, rather than to say weak. So James is not young, or James is not strong. Okay, well, that's done. That's it. That's all you're doing here. Okay? And that is De Morgan's law. Okay, let's skip ahead and do maybe a different one here. You guys are going to do 15 and 17. So 15. Let's do 14. Yeah, so actually, no, I can't do that. The only one that's like the one I assigned to you is the one that I assigned to you. So, blah, you can just do it. All right, and we already know how to do logical equivalences. So 25, 31, where are those? I'm not going to do another one. 57. Yeah, okay, cool. So I think that's pretty much it. There is one problem at the end that's a little bit more work because it uses a definition that you have to read for yourself. But that's fine. You can do that. Won't kill you. All right. So I think that's it for this lecture. Good luck with it. Come to office hours and ask questions. Hopefully you have plenty of time to do this homework. Good luck. See you next time.